Before I start talking about laminar flow, I just wanted to apologize. I looked at the videos that I had already posted for the other parts of this series, and I realized that the colors were not showing up very well. So I'm going to switch to Boreal black from here on out. I will hopefully be able to find a place where I can use those nifty colors because they're pretty nice. But for your reference, I've written down the equations that we've already talked about over here, in case you weren't able to see them in the other videos. All right, so let's talk about laminar and turbulent flow. Those are two aspects of hemodynamics that are important to understand. Laminar flow is what we want. That's ideal. That means the blood is flowing along the way it's supposed to, and I'm going to explain what that should look like in a minute. Turbulent flow means that the blood is not flowing along very nicely, okay? So in laminar flow, what happens inside a tube, the blood that's most closely associated with the walls of the vasculature is going to kind of be stuck. And every layer out will be moving just a little bit faster than the layer before it, so that in the center we get this really nice fast flow with blood zipping by, and on the outsides our blood's almost stopped. That's laminar flow. Okay, so this middle blood is probably zipping along. Turbulent flow, on the other hand, usually occurs when we have some kind of obstruction. It could be a valve, it could be a buildup of cholesterol, but that obstruction causes our red blood cells, or our blood, to flow turbulently. Okay, the flow is in all directions here. Ultimately, what that results in is a need for greater amounts of energy to continue the flow through this space, okay? And there's a nifty number here, our Reynolds number, that can predict whether or not flow will be turbulent. If the Reynolds number is around 2,000, flow will be laminar. If the Reynolds number is 3,000 or higher, flow will be turbulent. And we can use this nifty equation to help us to understand what kind of factors are going to contribute to more turbulent or more laminar flow. Okay, so first of all, we take into account the density of the blood itself, okay? That's not going to change very much, so we're not really going to talk about it too much, but it's important to realize that the density will contribute to the Reynolds number. Next, the diameter of the blood vessel, okay? This one's tricky. I'm not going to talk about it just yet, but I will get to it in a second. Next, we have velocity. Now, velocity contributes significantly to whether or not flow is turbulent. If velocity is higher, then the Reynolds number is higher, flow is more turbulent. If the velocity is lower, Reynolds number is lower, flow is more laminar. And then viscosity. Viscosity is inversely related to the Reynolds number. So if the viscosity is low, then we're going to have a high Reynolds number, turbulent flow. Viscosity is high, then we'll have a low Reynolds number, laminar flow. Now what increases viscosity? Hematocrit, okay? Hematocrit increases viscosity. Higher hematocrit, higher viscosity. Lower hematocrit, lower viscosity. Quick question, which of those will result in more turbulent flow? Higher hematocrit or lower hematocrit? It'll be the lower hematocrit, right? Lower hematocrit, lower viscosity, higher Reynolds number, more turbulent flow. Okay, let's talk about the diameter of the blood vessel, like I said we would. Contrary to what it appears, increases in the diameter will actually result in a decrease in turbulent flow. It's not correlated like it would appear to be in this equation, and I'm going to show you why. If we replace this diameter by 2 times the radius, and we replace velocity by using this equation by q over pi r squared, the area of this, okay? And then we follow that out a little bit. What we'll notice is that our radius kind of cancels out, and it actually ends up being on the bottom of the equation, right, for the Reynolds number. Because velocity is more important in determining, that's actually one of the reasons velocity is more important in determining the Reynolds number than diameter here. Okay, that's all I wanted to say on turbulent flow. I hope this was helpful to you. Thank you very much.